In section 17.1, we're going to learn about a new type of function called a vector field function. And this vector field function will be very important to us in this final chapter of Calc 3. Before we do that, let's review other types of functions we have learned. So we've learned about a real valued function of one variable, right? Y equals f of x. We saw this in Algebra 1, Algebra 2, pre-calculus, Calc 1, right? It's where you take one input, usually x, and get one output, usually y. And if you remember back to pre-calculus and Algebra 2, they would have you, pass the vertical line test and things like that. All right, then earlier in this course, we learned that you could take a vector valued function, right? You could take one input t and match it to multiple outputs. It could match to single points, x, y, in the two-dimensional plane, or it can match to three-dimensional points, x, y, z. And of course, it can actually go beyond that. We just have no capability of drawing anything past three-dimensional. Then in another chapter in this course, we learned that we could take multiple inputs, such as x and y, right, a two-dimensional point, or x, y, z, a three-dimensional point. Oops. Lost my brain there for a second. X, Y, Z. Here we go. There we go. X, Y, Z. Right, so this is 2D, this is 3D. And we can map it to particular a function that would only have one output, Z or W. So we've really gone both ways with this. We've taken a single variable t, called a parameter, and mapped it to two-dimensional and three-dimensional. And then we've taken 2D and 3D points and mapped them to new functions. But now we're going to take multiple inputs, such as x and y, or x, y, and z, and I'm going to map them to multiple outputs. So x and y affect both f and g. X, y, and z affect both f, g, and h. You're taking function inputs and getting function outputs. This last type of function that we're looking at is called a vector field. So it can also be written for three variables, so let's look at it. So this was written for two variables. If you look at it, it was x, y, x, y. So I'm going to write a vector function for x, y, z, 3 dimensions. If I could write a z there. And that would make a function of the x and y times I, or I'm just going to put it in bracket notation. Oh, and z, because this is 3-dimensional. So x, y, z. And then I take g of x, y, z, and that goes into the j component. And then h of x, y, z goes in the k component. So now we're going to spend a little time and graph one of these by hand. So we're going to think of the input as a position in 2 or 3 space, and the output as a vector to be graphed with the initial point at that designated position. So we're going to have an input as a position, right? So a point, position. And then we graph the output as a vector. All right, so let's look at how this works. Let's do an example. We are going to graph the vector field f equals xy. So this is 2-dimensional, you'll see, right? There's no z in that, thankfully, because this is very hard to do in 3 dimensions. And we won't do it by hand. We are going to have computers do this. All right, so we're going to take our initial point, which is our x's and our y's, and then we're going to have our vector form or from that initial point. And this is a particularly easy vector field to make because the point xy is the vector. Okay, so I'm going to start off with some rather simple housekeeping. First, I need to put an x and a y axis in this thing, so give me 1 second. There, now we have our x and our y axes. I kind of put them in the middle. Okay, so let's start off with points that are pretty obvious for us. Things like 1, 0, 2, 0, 3, 0. Okay, so over here on 1, 0, the vector is 1, 0. On 2, 0, the vector is 2, 0. And on 3, 0, the vector is 3, 0. Again, this is a very easy vector field because nothing's changing. So over at 1, 0, I make a vector that goes right 1, 0. At 2, 0, which is right here, I make a vector that goes out 2 like that. And at 3, 0, I make another vector that comes out like 1, 2, 3, like that. Well, that's a little bit hard to see. So let's look at another section. Let's look at 1, 1, 2, 1, and 3, 1. That would give us vector 1, 1, vector 2, 1, and vector 3, 1. Okay, so 1, 1 is this point right here. So I have a vector out 1 over 1, right? Over x, up y. So it goes like that. Starts at 1, 1 and goes over 1, up 1. Then at 2, 1, which is right here, I have a vector that starts at 2, 1, goes over 2, up 1. So it looks like that. And then at 3, 1, starts at 3, 1 right here, goes over 3, up 1, like that. All right, well, we did that. We can do, and obviously you can imagine there's tons of points you could fit in here. So I'm just kind of playing around. So 1, 2, 2, 2, 3, 2. So let's go up 1. So this would be 1, 2, 2, 2, 3, 2. Okay, so over at 1, 2, which is this point right here, it goes over 1 to the right, up 2. So it's going to end up here. At 2, 2, which is right here, it goes over 2, up 2. So it ends up right there. And at 3, 2, which is right here, it goes over 3, up 2, which is right there. And notice I'm only doing quadrant 1. If you wanted to do all 4 quadrants, you'd have to keep going in all the different quadrants. I know, it's a lot of work. This is why we don't generally draw these by hand. We're just seeing how this works for our own edification. All right, so 1, 3, 2, 3, 3, 3. I'm obviously picking up some patterns here. So this will be 1, 3, this will be 2, 3, this will be 3, 3. Okay, so over 1, up 1, 2, 3 goes here, and would go over 1, up 3. Oops. I was drawing that badly. Over 2, up 3 is right here, so it goes over 2, up 3 like that. And over 3, 3, which is right here, goes over 3, 3, which is right here. So notice the initial points are all in this little block that I've chosen for myself, and the points are going all over the place. It's spreading out, if you will. And just to complete the block, I'm actually going to do a 0, 1, 0, 2, 0, 3, even though the quadrants aren't that exciting. But 0, 1's right here, and it goes up 1, up 0. 0, 2 is right here, and it goes up 2, up 0, right? And over 0. And then 0, 3 is right here, and it goes like that. Like that. And you would do this to all the points in the grid, but nobody's got that kind of time. Right? So, of course, we are going to make computers do it, but we'll see that in a second. Now, this particular field is called a radial field. Can you see why? Everything is radiating out from the origin, right? Imagine the origin's your center and everything's bursting out from there. And all the other quadrants would work the same way, but pointing away from the origin, right? So the reason it's called a radial field is all vectors are radiating out from the origin. Right? Hence it's called the radial field. Now, what if we divided that vector field by the magnitude of that vector field? All right, so this would make every vector a unit vector. So instead of all the different lengths that we saw, they would all be length 1. It would still be a radial field. It would just not have this bit where some of them are longer than others. They would all be length 1. And then this one would have all the vectors shorter than that because you're dividing by the cube of the magnitude. So the farther we get away, so let me write this, all vectors, they get shorter the farther away we are. Get shorter the farther we are from the origin. Right? Because the distance becomes a large number, and then you're dividing by the cube of that distance. That's very useful for magnetic fields. Right? If you want to diagram a magnetic field, that can be helpful. Also, the negative of that vector field would be a gravitational field if everything was pulling in. Right? The farther you are from the origin, the smaller the pull. The closer you are to the center, the larger the pull. And it would be negative because, of course, instead it's like the opposite of a radial field. Instead of everything pointing outward, everything would be pointing inward on a gravitational field. All right, now this is a pain. So we are not going to be doing this. We are going to graph vector fields in Maple. Let's go look at them. All right, here's the first vector field we did. So I loaded with vector calculus and with plots. I believe you need both of them to make this work. And then I have the function vector field, and I told it the vector field was xy, and then I tell it that I'm in the Cartesian xy coordinate system. So you have to put that in there. And then it graphed it. Right? And I named that vector field that way. You don't have to do that. You can actually just go straight to field plot if you like. So I can do it that way as well. And aren't they pretty colors? I made it so it graphed with a color X, so the farther I go to the right, the more the color changes. And then I also did it here. Now in this case, I made the field strength equal to the log, which sort of looks like what it looks like when you divide by the norm. I did that here as well. So this is that vector field when it's divided by the magnitude. So when it's divided by the magnitude of xy, it looks like this. And notice all of those vectors are equal length. They're all length 1, unlike the original one, which has shorter vectors close to the origin. And the farther you get away from the origin, the bigger the vectors are, which is what we were graphing. So this one right here, this field plot, that's what we were graphing, this first one. These other ones are just kind of variations on a theme. Now, before I go farther and show you the answers to the questions they were asking about, I do want you to see that you can do this in 3 dimensions also. So I named my vector field right here, and then I said plot that vector field. So field plot, and it's graphing it, and it looks like this. Right? So it's radiating from the origin. That's a radial field in 3 dimensions. So this is x, y, z. And then again, I did a fixed field strength, so everything is the same length. This one, the closer you are to the origin, if you can kind of see it, the smaller the vectors are. And as you get away from the origin, the vectors get longer and longer. Right? That's naturally how that vector field looks. But if you change it so that you have a fixed field strength, then all the vectors are the same length no matter where you are. Nice, huh? All right, so you don't actually have to name the vector field if you don't want to, and I often don't. So I put it in here as field plot 0, x squared, and then I said from -5 to 5, -5 to 5. Now I'm not particularly fond of the color here, so I'm going to make it color equals y, just for fun. And let's see if, there it is. So now it makes it rainbow colored, which is nice. Of course, you could do color equals blue, and that'll make it all blue if you so desire. But I mean, where's the fun in that? I like doing rainbow colors if I can. Now, as for part B, so plotting -y, x, I just said field plot -y, x. Again, this is only 2-dimensional, and these are very intriguing ones when it circles around and circles like that. That's a special kind of vector field that we will talk about later. It's called a source-free vector field. And then I just wanted to see that you can do more and more with this. So for example, I graphed this particular plot in 3D, and then I said, hey, get me this vector field, and then plot the contour plot of that object on top of this vector field, and it'll do it. Right? And then you could have it do a gradient field, right? Again, graph the contouring plots and then graph, so that's the contours of this particular object on top of the vector field, and it will do it. So you can do a lot of things with vector fields, more than you could possibly imagine. But the upshot is use the field plot command to graph in 2D, right? And make sure you have with plots and with vector calculus loaded. And then field plot 3D will graph a three-dimensional vector field. And again, you don't have to name the vector field if you don't want to. You can actually just type in XYZ right here in bracket notation and it'll be fine.